Dr. Phys here, Theoretical Physics, Integral Trick 2, the Polar Coordinates Trick. Now this integral here, from minus infinity to plus infinity, e to the minus x squared dx, was once given to a friend of mine in college as a freshman. He had just learned, and I was taking calculus at the same time in a different school, we had just learned how to do e to the minus x dx, and in that case it'd be from 0 to infinity, so you have a finite integral. So we knew how to do that. But when you have the x squared, that complicates things, and we couldn't figure it out. It was very, very frustrating. An older brother of my friend, who was a physics major, graduate student, said use power series, but well, we couldn't figure it to this day. I don't know what he was talking about. I think he was wrong. So here, I learned this trick from a student that went to Caltech, and he told it to me in the car. We had no paper and pencil, and he talked it through in our heads. But here's the deal. What you do is you make this integral more complicated to make it friendlier. You actually say, I'm going to do a product of integrals. I'm going to do I squared. I'm going to integrate from minus infinity to plus infinity e to the minus x squared dx times the same thing. But now be careful when you have a product like this and you're going to integrate over a variable. Make sure you pick a different variable here so that you don't get confused with the x's here, because this is really integrate over x. That's its own thing. This is its own thing over here. Once when we do that, now things simplify, because you get e to the minus r squared. In polar coordinates, dx dy becomes r dr d theta, and to integrate over all the space, the entire plane, here you go x and y goes from minus infinity to plus infinity. To cover the plane in polar coordinates, you go from r is equal to 0 to r is equal to infinity, and you whip around all the angles. Theta go from 0 to 2 pi. So here the integral can be done fairly easily because you have the r in there. So we separate the integrals here. So you have the angle integral here times the r integration. And notice the r there is going to be friendly, because we'll put a minus 2 there and a minus 1/2 there. And that will take care of this integration easily. This first integration is just simply 2 pi. So here, e to the minus r squared over a negative 2, evaluated from 0 to infinity. At the top limit, thing knocks out, it's gone. And at the bottom limit, it's a negative, well, minus 1. You have to subtract it, so minus a minus a positive, and you get pi. What a fine result. And then if you take the square root to get your integral, you get the square root of pi. That is wild, all right? That the integration of the Gaussian over all of the x, the entire, all the x values, gives you an area under that curve as the square root of pi.